So, signal processing. I know, just there's plenty of different topics on this course. On the circuit part, today heavy stuff. Last week, quite heavy also on Arduino. Things, little things about Arduino environment. These are more like general topics that actually go around on any device. So practically you are not learning here how to make Arduino project, but here you are learning how to do or how things actually work. What are the building blocks? Okay, so let's see what kind of building blocks a digital signal processing part gives you. DSP, digital signal processing, means processing the sampled signal using digital methods. And oh boy, those methods are, they are quite mathematical and basically quite complex mathematics, complex ideas, but intriguing. Applications from audio signal processing, image processing, video processing, biomedical signals, seismology, speech recognition, anywhere where we have signals, actually there's a digital signal processing involved. Now, some of you may actually remember that notorious case of the submarine Kursk, Russian submarine Kursk, up on the North Sea. It was detected first by seismologists. So seismological, the stations recognized there was a happening on up north, undersea. So they could pinpoint using this digital signal processing, and this explosion was so big that you could actually hear it on seismological stations. I think about half of the hemisphere heard that one, and from that information they could pinpoint the location. So we are talking about powerful stuff. Unfortunate happening anyways. Typical DSP applications, well, they are filters. How to remove unwanted components of the sampled signal in the post-processing. So that is the most typical application. Couple of notes. The second note, there are special DSP courses in Metropolia. In the ICT, Jarkko Vuori is giving the digital signal processing class on, I think it was second period on fall, and then it's part of the embedded electronics course in for electronics degree program students. And the first note, you cannot fix unfixable, meaning on previous examples we had this data which was already broken by taking too few samples. You cannot fix that anymore. It's broken, the data is missing. So there is no such thing that magically bring back the information which was buried on that data. So basically it can be, DSP can be used for processing the digital signal. So if you need to do sampling, resampling at a lower rate, yes, DSP make a low pass filter and then sample that output data. Resampling filter. Okay. A simple low pass filter, which is the most common filter in in any case, the low pass filter to get rid of the highest spectral component noise. So if we have a relatively low frequency signal that contains some higher frequency noise, for example, in this one picture, there's a blue line which evidently has a little bit of noise there. And if you want to get rid of that spurious variation of the signal, then you can try something like a running average filter. In this example, the left-hand side of the table is the raw data with all noise on it, the blue. And then on the right-hand side, you take a few points average of these signals and calculate the value on the table. So for example, the average of, let's see, oops, average of those 5, I think that is calculated maybe here, hard to tell, maybe that one. So all of these points are on the right hand side are made by taking the running sum of few points on the left hand side. So subsequent samples, average, and that's your output. And yes, it was a moving average filter. And as you can see here, the red curve is smoother. It does not have that variation. Just be careful there that you don't remove a real thing that you think is artifact. So not always the high spectral things are not always the noise. It could be also the signal. But anyways, the previous slide, moving average filter. Here we have the frequency responses, or actually amplitude responses, drawn on a very funny linear scale. Usually the frequency response is actually shown on the decibels on amplitude response, and frequency response is in logarithmic scale. But for digital filters, this linear scale frequency is okay. But anyways, simple thing. You take a sample, put in the buffer, then calculate the average of n most recent samples. Simple thing to do. So takes only a couple of lines of code to do. The frequency response or the amplitude response actually depends on how many points you take. On this picture, you can see if you have 3 points, then you don't really get too much of the filtering there. There's still quite a lot of noise. When you go up to the 31 point, then basically most of that data is on DC component. On the other hand, you may actually at some point start losing the data itself. It's always a compromise. And then another one, which you can see here, there are these notches where the amplitude response goes to 0. There are some special frequencies on that average filter which do not pass the system at all. So in principle, if you have, for example, 100 Hertz frequency, you can match your sampling rate so that, for example, 3-point average will remove that 100 Hertz extra signal totally. It can be done. A little bit tricky, but can be done. Okay. Anyways, low pass filter, simplest one is moving average filter, where you just take a sample as input. So you have the collection of input value history. And when you get a new value on that table, you calculate the average of the most recent samples, and that's your filter output. Okay, now I have two core segments, and there's very small difference, but anyways, this is a remarkable difference on the sampling. On both codes, we have this remaining part. We have the calculation of sum. Okay. Audio problems. I don't quite get it. Why do I have these audio problems? Okay. Okay, fine now. It might be just my headset was not correct. I tweak it a little bit. But anyways, so yeah, back to this picture. So the end of the program is the same, where we have calculating the running sum, or calculating the sum of 3 points and printing out the value. The first one is reading this data and then 3 samples and then moving on, and then calculate the sum and then do stuff. Okay, the rightmost is reading one value on each loop, one single value, and putting it somewhere on that buffer. And somewhere means that it basically rotates that index. So this is actually a circular buffer here. If you have heard the term circular buffer, this is exactly the thing. So when you are reading a value, you put it on the next, the possible place on the buffer, and it also overwrites the previous value. Okay. Which one do you think will be work as a 3-point running average filter? This is quite obvious. It's the right-hand side. The problem with the left-hand side is that it reads on every loop, it reads 3 values. So maybe I should actually do the timing diagram on timing diagram. So timing diagram on left-hand side loop goes something like this. It goes and reads those 3 values, then calculates the, maybe I should mark. Then it calculates a sum, and then it goes and do stuff with the value, do stuff, which could be, for example, like this, very long time doing stuff. The rightmost, and then okay, then repeats the calculate, and do stuff. It works like this. On the right hand side, we are measuring, saving on certain place. Then we calculate, do stuff. Measure, calculate, do stuff, and so on. So practically what happens, this on the left hand side, you are basically on the same problem as you were on this meteorological station on Spokane. You are taking rapidly samples, but basically they are about the same values. This one doesn't really do much of anything. And you are still giving just the average value of this sample here. In here, you are in principle, you are always giving the 3 points average. So you are averaging over 3 points constantly. So this one actually works as it's supposed to work. This one works as the person who wrote it just happened to write it. There we go. So right hand side much better, or makes more sense. Let's put it this way. So yeah. So basically, when done correctly, every time you sample a value, you also produce a filtered value. Yeah. So remember, on this signal processing, when it's done correctly, you do it always like that. Sample and then produce a value using filtering. You can also do resampling at a lower rate. Then you would do lots of filtering for each single output. But that's different situation there. All right, so good way and bad way. All right, timer interrupts for sampling. A great idea. Excellent idea. That's exactly how you're supposed to do the sampling. This guarantees that samples are at the same intervals, which is the foundation for digital signal processing. There is a state of art on variable rate signal processing, but in any other case, you always assume that you know that sampling rate and it's uniformly distributed with constant sampling time, the same intervals over and over again. And this is, well, why we do it. We don't want to have extra complexity, and it goes really fast, very complex. Okay. But anyways, yeah, we don't do it with timer interrupts. We are working in Android. You learned a little bit of the timer interrupts on the fourth exercise. And I don't know if anyone actually found it really fun exercise. The pin interrupt was simple. But for timer interrupt, you needed to do some stuff on the registers. Okay, when you start doing these timer interrupts with A/D converter, you run into kind of big trouble of nested interrupts, which is basically no on embedded coding, and there are techniques how to avoid that one, but those will be next fall courses, I think. Or actually, you are now on taking chaos computer architecture, I think. Okay, you have been told already that this is not too straightforward. When you start talking about interrupts and timers and such kind of things. But for this course, we are not paying too much attention to this one. We keep things simple, meaning Arduino simple. And okay, troubleshooting remotely with virtual equipment, not real equipment. Not fun. So no, we are not using time interrupts for sampling on this course. After this course, you should be using always timers for making the constant sampling rate. Okay, and that's basically about the signal processing part. So we had D2A converter first, how to make a analog output. Then we have the A/D converter, which is in Arduino very simple. You just get the value from the bin, and then we add some digital signal processing fundamental parts or principles, basics. So the main point is there to have that darn running average filter. You will get ideas of how to make better filters later on next fall. But then you would also have different platforms. You will be using ARM processor platforms, which are more capable. And now we go to the PWM, which is the pulse width modulation. What is pulse width modulation? Well, just like what it says, you modulate the output so that basically the value of the output is proportional to the duty cycle or pulse width. Okay, so on this picture we have a train or sequence of pulses with the varying pulse width. On the beginning we have shorter pulse width with the same period. See the constant period from here to there. It's the same also in here. So the period does not change. Pulse width, lower pulse width here, longer here. So in average, the signal is lower here than there. Simple. The ratio between the pulse width and the period is called duty cycle. And that can be anything from 0 to 100%. So basically how much of that full period is covered by the pulse. And this is actually a nice way of controlling how much power is delivered on average. For example, if you hear are running this pulse width modulation and run directly an LED with this pulse width, you can actually have a simple dimmer logic there. So you can change from say dim light to bright light by changing this pulse duty cycle. Okay, so pulse width modulation is control of power on average. Suitable for controlling devices 0 to 100, well, yeah, either on or off. So this is quite like some people are driving. There's two positions of the gas pedal. It's either on or off. Okay, but anyways, so some examples. I already mentioned that LEDs. This is the way you are controlling white LEDs. You don't put any resistors there, since resistors consume power. In here you get the same effect of dimming by running either 100% of the current to 0% of the current, so you can get the light brightness control without any resistors. So you are consuming power only on the LED. Another one, microwave oven, have multiple power levels, but in reality, the magnetron, which is the radiating element there, it's either on or off. It's designed that way. It does not really, you cannot drive it at any other power than what is designed. So that's why in some of these the microwave ovens, when you turn it, say for example 60% power, then you can hear different noises. So you can hear the duty cycle when the magnetron is switched on and then off. There's a humming noise when it's on. Okay, so again, PWM controls amount of power delivered on average, or actually when you combine that PWM with an analog low pass filter, you have digital to analog converter. So you filter out this not totally, but most of that high speed variation, meaning the pulses itself, so that you can see only the envelope. Okay, PWM, way to control power. In Arduino Uno, there are only the it has period, or actually the frequency is fixed. So 980 Hertz rate, or for pins 5 or 6, and other pins around 490 Hertz. And with a fixed frequency, there are some challenges. Well, if you want to have any, if you really have to have higher PWM period than that, then you cannot use Arduino Uno anymore. You need to use something else. And also 980 Hertz, if you run anything that has mechanic resonance, 980 Hertz is very obnoxious sound. It's around 1 kilohertz. They are really nasty sounds. But anyways, there is a PWM, the output you can play with. And how to enable PWM out is actually you call analog write pin. So practically the analog write is using PWM controller for the output, and analog output pin means PWM. If you want to have steady PWM, you need to also have a RC filter after that. And of course, if you're using the PWM, then you need to set the pin mode accordingly, so it'll be output pin. So then it can give some current out. There are more details on PWM tutorials on Arduino. So PWM frequency, how to set up the base period time. It's application specific. If you have a light control like LEDs, light control, if it's too slow, then PWM is seen as flickering. By the way, if it's close enough to some video sampling frequencies, so say around 24, 25 hertz or 50, around 50 hertz, less than 100 hertz, the frequency, then you can get funny blinking lights on videos when you are actually looking at some, say, LED light with your camera or something like that. It can show flickering. Depends totally on what frequency you are actually using on PWM. But anyways, too slow PWM is showing as flickering. If it's close enough to another lights, then you can have funny interference effects. Such kind of considerations you need to be aware of. Audio, too slow PWM, well, it's noise. It is periodic signal. On audio output, you should keep the PWM frequency higher than the hearing range. So above 20 kilohertz. 20 kilohertz period. Okay, again, next week we are talking about the transistors. PWM, if it's high, then basically field effect transistor in particular, they can actually stay in half conducting state, which means that it may cause heating of the transistors. So when you are switching any transistor, you need to keep those as fast as possible. But anyways, more about that next week. And if, of course, PWM, if it's on radio frequencies, then that can actually end up being electromagnetic interference to other devices. So something to also remember when working with the PWMs. Demonstration. Wow. Let's see what kind of demonstration we have. Okay, and the code. Just pin mode set to output and then analog write to pin 3, value 10, start simulation. So that's what it looks like. Okay, that's what a this PWM actually looks like. Then let's stop the simulation, put some other value there, for example 100. Was it actually the full deal? Let me put that 50, a longer pulse width. Okay, great. Even more, so 150 as the, okay, so the pulse width just changes, not a big deal. So this is fun. Oh, well, very educational. So, and at the same time as I change this width value, if you compare the brightness of that LED, it's a little bit dimmer. If it was a real LED, you could see the change, but in here we are just the simulation environment. It doesn't really work that well. But anyways, when driving an LED, you can change the brightness of the LED accordingly. There. Now it's evidently brighter. So, yeah, it controls directly the power. On last session about the AC circuits, when you think of the average power of a digital PWM circuit, you are running it either on or off, which means that on PWM, if that is the full cycle and 100% and this is 0%, okay, so this 0 to T and this is small t, so that's what you're varying. If you think of the power, which is average power 1 over t, 0 to full t, and ut times it dt, that's the average power, okay? So practically this one here, when you have just a resistive load, which is 1 over t, and then you have one integral from 0 to t, which is on. You have the u0 squared times divided by r, for example, like that. So that's the full power, and then you have plus 0 to t. 0. So here we have a 0 signal. So practically you have this power control so that you have the maximum power times the period time, what is that? Duty time, which is the duty ratio here. Okay, so direct control of power. Yes, one small tool, serial monitor graph. I already showed a quick peek of the serial monitoring graph. So serial monitor is able to do graphing. If you have numeric values coming out from the serial port at any form, then basically by clicking that one button on the right lower corner on serial monitor, you can see the graphic, this as a graphical. And then there's also pro tip. If the this graph actually looks messy, then clear it. It may actually start from a funny point. It seems that sometimes it misreads the first values and basically starts on the funny scale, but basically if you hit the clear and wait for a while, that usually fixes it. Another one, I don't know if you know already that, but if you want to have a graphics copied fast from your screen, the Windows Shift S will give you actually a opportunity to pick any part of the window to your the scratch pad and use that one, for example, as a answer to the exercise. Small tip. Ha. So now it would be the exercise time. Let me go through of these 6 exercise questions. Assignments number 6 on Arduino analog input and PWM. Okay. It seems that this is exercise 6. There's a small typo here, so don't worry about that one. You don't need to worry about that. So actually, let me change that one to 6. Good. So analog input with software filtering is the first part. What to do there. So we actually have the analog. Wait a minute. How do I get that one a little bit lower? Create this circuit. So we have analog input coming from a potentiometer. One end is tied to 5 volts. Another end is tied to ground. Then we are measuring with voltmeter. We're measuring this resistor, variable resistor output, but it's also, you read the same value also on analog input pin A2. And the task here is to try to get match on what this the Arduino is reading in volts and your multimeter. So this is the software you need to implement. First, initialize the serial port. In the main loop, you're measuring the analog voltage on the pin, means analog counts, analog input counts. Then you convert the ADC counts to volts. And yeah, it's not that straightforward as it sounds like. The count is in integers. I mean, if you in a code you divide it by an integer, then basically you can end up having a losing some data. There's a good example down here. If you on compiler, C compilers, if you type 1 divided by 10 or a variable, integer variable 1 divided by 10, it will equal to 0 because the compiler thinks that these are integers. So how to force floating point numbers is to actually calculate this one as 1.0 divided by 10.0. Then it will be resulting a floating point 0.1. Okay, that's one thing. And way to use it? Well, how about in here? Voltage equals ADC count times reference voltage divided by bits. That's a good place to use it. Then print the current volts on the serial port. That's easy. There are a couple of examples already there. And then only one value per row. So there's a line print function. Then slow the process down. Otherwise, you will have lots of stuff going through this serial port monitor, and which don't give much of the extra information. It just slows down this simulator environment. So practically, you can pick your own favorite delay there to slow down the loop rate. Something like 10 to 20 hertz sounds about right. And the test is that you see the same values on serial monitor in volts as you can see on the voltmeter on this Tinkercad. Yep. So also you could check the graph tool of the serial monitor. So let's see. Yeah, this is actually a pretty good place to start. It already has the this input for some other popo, but anyways, it has the serial monitor, some delay there, and oops, then you can play with the values. And now your task is to match this value with the multimeter value. Okay, good. Some source code would be nice. Analog sampling with floating input. Ha 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 ha. What happens if you leave a signal open, a analog input pin open? For example, here I have a signal on A1, but how about if I use analog input 0 instead? Okay, something like that happens. So it's totally different then. So practically you do just about the same thing. Don't put anything as an input and see what happens. That's typically what happens also in real life. So yeah, floating pin means that you really don't know what is the voltage on input. Same thing also if it was a digital input. You never know what is the voltage on a digital input if you leave it open. All right. Part 1C. Analog sampling with digital software-based filtering. So on your original design, which was something like this, now you know that, okay, my voltage monitor on Arduino works well. You don't need any more this voltage meter, but instead now you give an extra noise from function generator. So this gray box here is a function generator which produces a, for example, sinusoid waveform certain, and you will do a resistive adding circuit here. So this voltage is now combined with this higher frequency kind of noise signal. And you can observe that signal with the oscilloscope. Okay, why to do this? Well, this is about experimenting with low pass filter on also low pass digital low pass filter. So that signal came as it is to the analog input. We cannot do anything for that one. That's real data, except that we can go and start filtering it with a moving average filter. So yeah, practically implement a moving average filter with different filter lengths. How to make the moving average filter? Well, that was basically on the first part of today's lecture. There's a code that could work, maybe, I don't know. It may work, but anyways, you need to understand also there how that ring buffer, how these numbers actually affect on the size of the ring buffer, that kind of stuff. And then basically your task is to measure the amount of noise and make things as fast as you can, and some key points there. You can read these. So continue. Set the potentiometer to middle position. Set remove delays. This needs to be run faster. Serial port speed also make it faster, so that otherwise your serial port will be the bottleneck here. It cannot send fast enough so that the process would actually would not need to wait for that the transmission. Yep, and instructions continue, and a couple of pictures what it should look like, something like this, similar to this, not exactly like that, similar to that one, since all of you have different frequencies on that noise, of course, which means that these will differ. Sample graph when you have raw data, meaning average of 1. And then basically do the same graph for average of 3, average of 7, and average of 13. They should practically, you should observe this variation of the signal going down. Exactly the same way as on this lecture part examples, filtering with the running average will reduce the variation. There. I know there's plenty of things to read here, but anyways, this is quite straightforward. You just need to follow the instructions, and there are plenty to learn on also on this explanation part. What else? Yeah. What is the noise amount? Okay, that you can estimate the noise, the size of the noise in volts or millivolts. Write the answer, and you should see the reduction of the noise level when your filter length is higher. Yeah, and some space for the graphs with different lengths. Okay, that's the running average part. Digital filtering, simple digital filtering. The last but not the least, simple digital control. We start from this kind of circuit. So what it looks like? It looks like there is pin number 6 is actually a PWM pin. Okay, PWM pin. There is the leftmost oscillator. Oscilloscope is showing the waveform, and after that you actually have a capacitor to ground. Okay, R and C. That sounds like low pass filter. Yes, sounds like a low pass filter. So in principle, after this one, you can see the voltage output, filtered voltage output is 3.3 volts or 3.03. Okay, and you can also see the oscilloscope output of that same pin here, same part. So okay, oscilloscope showing that looks like DC at, let's see, 10 volts total. So okay, that DC level here is about 3 volts. There's some variations. Okay, good. So, and then there's something extra. This LED from the same point. So this LED with a resistor acts as a variable load. You can turn on or off this load. It's either on or off depending if you're pressing the button or not. So it's basically kind of extra load for this RC filter. Right. Where was I? Here. That's a connection. And the idea here is actually we will create a system that always creates 3 volt output regardless of the connected load. So this is called actually a voltage regulation. So this is a simple voltage regulator made by Arduino, meaning, for example, similar devices you already have. You have these nice the extra power supplies for mobile systems, which gives you 5 volts, and in USB output, whatever you have in as a load. It may have a small mobile phone or a smaller device. It always gives you that 5 volts output. So it's a regulated output. And okay, how to do this? Well, in principle, you are here with the A to D converter. AD converter is connected to this charge bank. Okay, So this one measures the voltage at this point. When you are measuring the voltage, then you can either make this duty cycle of PWM either higher or lower. You can adjust the duty cycle so that if you have lower than 3 volts on output, then basically you will make your duty cycle higher, and it's higher than the 3 volts at output, then you make this duty cycle a little bit lower. So that's the fundamental of a control circuit. So it tries to keep that voltage at output, or the measured point voltage at certain level, whatever happens. Okay, and then some extra text here. What to do in the loop. You can read it. You should be able to do this if you read it and think how it should work. Typo. And making the there, and how your program should function, and how to test this one. So it's not just that you get that 3 volts there once, but basically when you press the button, meaning you are then having an extra load to the circuit, this LED and resistor actually are the extra load for this circuit, then the voltage drops immediately. But your program should compensate that by raising the duty cycle. So when you keep pressing the button, it should eventually get into the 3 volts level again. When you release the button, the extra load disappears, and immediately this voltage actually rises higher than 3 volts. Then your program should notice that one start decreasing the PWM output. So in that sense, this is very simple or simplified P controller and, well, proportional controller. So next week you will continue from this one and create a more real voltage regulator. Okay, we are not quite sure yet if the simulator actually allows to do it, but that's the plan. Make a more realistic voltage regulator, which is practically quite close to what is inside of the power bank or any other regulated power output. All right, so that was the Arduino part of today's lectures and stuff. So, do you have any questions at this point? You have question about 1C. Okay, let's take a look at the 1C was about, was it that one? 1C. Yep. Okay. So the 1C, what about this one? So there's the connection. The details of the connection settings are found from the text. And basically the key points and minus 40 and plus 40. Oh. Okay, that number here, 1000. Okay, you will definitely see your own values there. So, but hetkinen, oh, wait a minute, my average is between minus 40 and 40. So do you have similar to this one? How did you get negative values there? Strange. Okay, in here, in this picture, actually, the should I actually run this for just for fun? Just for fun. See. Oh, do I have it already? No, I have that part. Okay. Just a moment. I will. Let's do it. Let's do it this way. Arduino. Okay, there we go. Potentiometer I have on different place though, but doesn't matter. And that at the middle point first. Oops. 250 kilohertz. What it should be, it shouldn't be 250 kilohertz. A kilo ohm resistor. What was the resistor size? Did it say anything about the resistor size? Okay, here we have the voltage 1 kilo ohm. Potentiometer 1 kilo ohm potentiometer, then alrighty then I should have the resistor of, oops, was there already, resistor and a capacitor. Do I have capacitor? Capacitor, not capacitor in this one. What I'm talking about here. Hehe, hehe. Sorry, I make a big mess here. Try to be fast. Oh. And where's the, where did I lose my parts? Oh, there. Okay, found it. Oh, that resistor, a couple of resistors, and those resistors were what size? I think they were also there. Also 1 kilo ohm, at least on that picture they are. And then I have oscilloscope, function generator, and oscilloscope. that signal is fed through via this resistor. These are connected together to have the summing there. Oops. Maybe A1. Oops. Oh boy. My control button is starting to act again. All my fat fingers, either or. This looks really ugly. Never show these kind of things too as a result. Okay. Still around 225. Is that okay? Maybe. You actually have different frequencies. So SSS number also affects on the real numbers. However, the effect of this should be just about the same. So let's measure the voltage. Where at that point at input, yes, which is basically same as here. Maybe that is fine now. And then start the simulation with some values. Okay, function generator. I'll just put, say, 200 hertz here, 1 volt, 0 offset, oscilloscope, 100 milliseconds, 400 hertz. Well, I'll just try that one and maybe okay. So the signal itself looks like, okay, remember also to have the sinusoid signal. That's one part, and that should actually then provide some. Did I have a code here? Yes, I did. Okay, stop the simulation and let me try to run it as fast as I can. Okay, I got with this, the average is somewhere around that one. Oh, okay, stop simulation. Wrong pin. Doesn't make sense. Okay. Now, in my case, I got signal between 180 to 300. So I would guess your numbers are just okay. Nothing to worry about. As long as you get something which is similar to that, although, another thing, small details. There's devil in details. Bitrate fast enough so that you don't get aliasing. Yep. Something like this. So you would get different values depending on basically if this is exactly here or is it somewhere else. As you can see, when you turn this resistor knob, you get different kind of signals, of course. And of course, the frequency also changes the behavior. There. Any other questions?